Hipparchus, the Greek astronomer and mathematician who lived more than 2,000 years ago, used the solar eclipse to solve a celestial geometry problem. He knew that at a spot in northwestern Turkey an eclipse had totally blocked the sun. But in Alexandria, about 600 miles away, only about 4/5 of the sun had been covered. For that tidbit, he calculated the distance between the Earth and Moon to within roughly 20% of the correct figure. Hipparchus was among the earliest scholars to take advantage of eclipses for science. In more recent centuries, scientists have used these celestial events as opportunities to study the solar system, especially the sun itself. Usually, the sun is too bright for scientists to see anything in its immediate vicinity. Only during eclipses does its radiant halo, the corona, become visible. A total solar eclipse showing the sun's corona in Brazil in 1919. Science Society Picture Library, via Getty Images in 1605, the German astronomer Johannes Kepler mused that the corona observed during an eclipse might be a consequence of an atmosphere around the moon scattering the passing sunlight. Eventually, scientists figured out that the corona surrounded the sun, not the moon. Observers also reported gigantic arcs rising out of the sun, solar prominences now known to stretch hundreds of thousands of miles into space. The invention of the spectroscope in the mid-19th century brought new solar discoveries. A glass prism splits light into a rainbow of colors emitted by specific atoms and molecules, barcodes, in a way that identify the elements making the light. In 1868, a French scientist, Pierre Janssen, traveled to India to view an eclipse through a spectroscope. The sun's prominences, he concluded, are largely made of hot hydrogen gas. But a bright yellow line seen through the spectroscope, initially thought to be an identifier of sodium, did not match the wavelength of sodium. That signified the discovery of helium, the universe's second most common element. It would not be found on Earth for another 13 years. The observatory of Norman Lockyer on the Kent coast of England in 1890. Lockyer is one of the scientists credited with helping discover helium. Science Society Picture Library Getty Images left, a photograph from 1878 of the sun's surface, left, that was taken by the French astronomer Pierre Janssen, right. Left. Science Society Picture Library, via Getty Images, right. Oxford Science Archive print collector, via Getty Images. During a total solar eclipse in 1869, two American scientists, Charles Augustus Young and William Harkness, independently observed an unexpected faint green line in the corona. Scientists hypothesized it might be the emission of a new element, which was given the name coronium. It wasn't until the 1930s that researchers realized coronium was not a new element, but rather iron with half of the atom's 26 electrons stripped away. That finding hinted at ultra-low temperatures on the sun, and at a new mystery. The lines of color seen on a spectrometer can also be used to measure temperature. The temperature of the surface of the sun is about 10,000 degrees Fahrenheit. Yet measurements of the corona, begun during a 1932 eclipse, put the temperature there much higher, millions of degrees. Ever since, solar scientists have been puzzling over precisely how the corona gets so hot. Eclipses have taught scientists much about how our solar system works. But the events have also brought down some firmly held ideas. Astronomers long ago discovered that Mercury, the innermost planet, wobbled in its orbit more than Newton's laws of motion indicated it ought to. In the 19th century, many thought there must be another little planet inside the orbit of Mercury that was pulling it around. They called it Vulcan. Various observers reported seeing a small dot cross in front of the sun, and many were convinced Vulcan exists, and its existence can no longer be denied or ignored. The New York Times reported in September 1876, during the darkness of a total solar eclipse 2 years later, two astronomers, one stationed in Wyoming, the other in Colorado, separately claimed to have spotted planets within the orbit of Mercury. But they were wrong. They probably had seen well-known stars that become visible in the darkness of the eclipse. By the end of the century, most scientists doubted Vulcan was there, and in 1915, Einstein's theory of general relativity provided a plausible explanation for Mercury's wobble, a distortion in spacetime caused by the sun. Einstein's ideas set the stage for the most famous eclipse experiment of all time, in 1919, during which Sir Arthur Eddington observed the bending of starlight around the sun. The findings verified the theory's predictions. Solar eclipses have been used not just to deduce what is going on in the solar system but also to study Earth. In 1695, the astronomer Edmund Halley discovered that modern calculations did not quite predict eclipses reported in ancient times. As it turned out, that is because the Earth's spin has been slowing. Science Society Picture Library Getty Images Chinese historical records provided clues needed to figure out how much. In the 4th century BC, a Chinese philosopher, Mozi, wrote that the sun rose at night, describing an epic battle that had occurred about 1,500 years earlier. While paging through the text at the University of California, Los Angeles, a couple of decades ago, Kevin D. Pang, a former NASA scientist, realized this was not a poetic account of a fiery combat, but a description of a total eclipse. The eclipse, which occurred close to sunset, indicated a passage into night, and the re-emergence of the sun was thus a sunrise at night. The day and place of the battle were known. Computer simulations determined how much slowing of Earth's rotation rate was needed to make the shadow of an eclipse that occurred that day pass over the battlefield. If the Earth was spinning faster back then, the day was shorter, by 0.07 of a second. Eclipses also provide a test of weather models. We're not normally in a position to turn something off and see what the response is in a nice cause and effect sort of way, said Giles Harrison, a professor of atmospheric physics at the University of Reading in England. When the sun disappears, temperatures drop and winds calm. Using weather station data from the 1900 eclipse that crossed North America, a meteorologist named H. H. Clayton noticed that the winds also appeared to change direction. During a 2015 eclipse in England, Drive, Harrison and a colleague analyzed weather station data and collected observations from several thousand citizen scientists. They found that the wind direction shifted 20 to 30 degrees because warm air had stopped rising from the ground. That largely confirms Clayton's thinking, his ideas from over 100 years ago, Dr. Harrison said.